Okay, we see Christian Bühler and Anna Wagner. Welcome to our next presenters. We heard about the buzzword traceability quite a lot during the last minutes, and now we will take that buzzword and lay it deeper within our next presentation. So we have Anna Wagner and Christian Bühler in the call today for you. Anna is a senior consultant at ProStep and is the product owner for Tracy. And Christian is the manager for validation and verification at ProStep as well. And the virtual stage is yours. We are looking forward to your talk. Welcome.
Thank you very much for the kind introduction and welcome to our presentation, Traceability and Collaboration. As you heard in the previous presentation, we got a lot of information about the credible simulation framework. Next slide, please. Next slide, please. Now it's our pleasure to show you how we proved the industrial applicability of that framework, the challenges and best practices identified during the workshops, as well as ProStep's traceability software demonstrator, Tracy, which is developed within the set-level project to support collaboration and ensure traceability across the development process. Next slide, please. So let's start with a short motivation. Today we see an industrial trend towards digitalization and virtualization of product development processes. And this leads to approaches where more and more decisions are based on simulation results. Therefore, there is an increasing need for credible processes and standards which support the simulation-based decision-making. In addition, we also see the trend towards joint developments, which is especially true in the field of automated driving. To give you an example, the joint development of an automated driving function that includes a camera model as the perception part of the overall function. And this use case shows the need for close collaboration and coordination between the partners involved. In contrast to former approaches where the camera model, let's say, was only contract work. And the next slide, please. So, as I pointed out in my last slide, there is a trend towards collaborative developments. And the set-level project developed the process to support the collaboration between partners in the area of simulation-based engineering and testing. This collaboration process is always composed of an agreement process and a development process, which you can see here on the right. It starts with the agreement process, which is used to clarify and to define the technical and contractual boundary conditions. And after the agreement process is finished, the actual development process starts, which covers the joint specifications, designs, implementation of simulation and modeling tasks. And is in our case represented by CSP and CMP, which you heard in the last presentation. And the next slide, please. To ensure the industrial applicability and to prove that the process supports the industrial collaboration, several workshops together with our set-level industrial partners were conducted. The first part of this workshop series were joint workshops where all involved partners come together to discuss the process in general and to create common understanding of that process. After that, we split into separate groups and workshops where always two partners, OEM and tier, as you heard before, discussed the process in detail with focus on the collaboration. And the results of these workshops included a collection of experiences from our partners, which have more than 10 to 20 years of experience in the field of simulation. The discussions on improving the use of set-level processes helped us to answer questions. For example, are these processes or are the processes developed within set-level really applicability in the cooperation between industrial partners? And another example, which elements and steps are critical in collaboration and cooperation? And the next slide, please. To Together with our partners, we gathered more than 300 individual feedback items during these workshops. And you can see a consolidated Miro board on the right. And from this large amount of information, we prioritized the key findings together with our partners. But even the condensed findings are still far too much for this presentation. But let me at least show you some of the key findings. Looking at the agreement process, we have to realize that often few simulation experts are involved in that phase. Another common problem is that models and simulation environments are often redeveloped. The limited reuse of this leads to avoidable extra work. And finally, end-to-end traceability for building the digital thread throughout the entire development process becomes crucial if we want to secure more and more ADAS functions through simulation. And then the next slide, please. But we have not only identified problems and challenges in the discussions with our partners, we always focused on solving these problems and tackling the challenges. And this brings me to the collected best practices. As before, I can show you only an excerpt of the findings. The solution of the first problem seems to be rather straightforward by simply involving experts in the agreement phase. However, this is not so simple because this is a company decision. So the management also needs to be aware of this problem. Further, the reuse challenge can be addressed by establishing and using domain-specific standards for technical interfaces, model properties, and so on. And here, the further development of such standards has been an important part of the Z-level project. And I think all of my colleagues who worked in this field are proud to show their outstanding results, share their outstanding results in this field in their own presentations. So the last challenge, the building of the digital thread could be achieved by using a suitable process. And this could, for example, be the CSP framework or the CSP process. And this is also the this is also the reason why we wanted to ensure the industrial applicability of this framework. In addition, the application of such a process should be tool supported. But at this point, I do not want to preempt the second part of this presentation. So if you'd like to learn more about the collaboration process, the CSP framework, the best practices and challenges we gathered, or discuss with our industrial partners about their key findings, you are invited to visit us at our booth 19. And at this point, I would like to thank all partners involved, our industrial partners and all the other partners for their great work and the fruitful discussion. And here, because my voice is also not the best, so finally I'm done with this part of my presentation. I will hand over to my colleague Anna, who will tell you more about the tool-based support for collaborative development.
Thank you, Christian, and thank you for pulling through with your voice. So to pick up where Christian left this presentation, I would like to talk about how tool support can help create traceability in the area of simulation. The goal would be to create a continuing and unbroken digital thread across the entire credible simulation process and beyond, if necessary. Doing so would require the supporting tools to implement at least 3 functionalities, which we would like to pay special tribute to within this presentation. First, the already mentioned issue of reusing existing artifacts and configuration items must be addressed to minimize redundant and thereby error-prone work being done. This reusability would, ideally, even include automatically updated usages when changes are being made on the original artifact, or at least automated notifications to the users that a newer version is available. If they desire to switch it, they can then switch it manually. Hence, the tools can ensure that the correct information is being used and referenced, while also spanning a network of information across multiple simulation projects. Second, supporting tools must enable users to re-simulate previous simulation results. This requires some sort of version control over the applied artifacts, reasonings, and other input items to simulations, and may even go as far as storing information about the simulation environment and its configuration. Only then the provided information can be trusted fully by users and, especially important, third parties, for example, during audit processes. Last and definitely not least, credibility is also about being able to observe traces between artifacts that are not directly related. This could, for example, be a trace that is drawn between a requirement at the very beginning of the credible simulation process and the eventual simulation result itself. It is obvious that such traces, just as the information and artifacts themselves, are not bound to a single source system, but may be spread between multiple source systems and create connections between them. If I could have the next slide, please. As if enabling credibility by ensuring reuse, resimulation, and trace observation would not be hard enough, the aim of said level was to demonstrate how this endeavor could be implemented by a variety of tools that may or may not be combined together along the credible simulation process. More precisely, we identified several use cases for supporting software tools during the different credible simulation process phases and demonstrated how these tools could be chained together. This includes a tool to execute simulations, such as the PMSF FMI bench, a tool for quality assurance, a tool to define simulations and their parameters, like the Orchideo Easy SSP by Excellent Solution, and of course the demonstrator we are presenting today, the traceability tool Tracy that we at ProStep developed within this project. To communicate between the manifold of potentially supporting product tools, the STMD standard and SSP containers are being used. By exporting the entire information packages, for example, between EasySSP and Tracy, users are not logged in and the call for appliance of domain-specific standards is being answered. The findings of the traceability demonstrator Tracy are now being used as a basis for developing ProStep's most current commercial product, OpenCLM. On the next slide, I would like to dive a little bit into our traceability tool, Tracy. This tool aims to empower cross-partner and cross-application collaboration while maintaining credibility. By addressing the three key features discussed in the previous slides, Tracy creates a digital thread across domains and allows both for forward steering and backwards tracing. In detail, it guides users along the credible simulation process and its workflow and enables them to monitor the current progress and recent changes. At the same time, dedicated impact and traceability analyses can be performed on the available data. Baselines can be used for resimulation and audit processes, and a powerful search helps users to manage large simulation data. Overall, Tracy aims to interlink information from various source systems and is currently able to connect, for example, to Git, Windchill, Doors, and Jira. For connecting source system, the tool builds on open standards such as OSLC and ProStep's own interfaces via OpenPDM, enabling the connection to tools that provide OSLC interfaces or that can be integrated via OpenPDM connectors. The next slide, please. But instead of telling you on more slides what Tracy is about, we would much rather like to take you on a journey to experience the capability of our traceability demonstrator yourselves. For demonstration purposes, we have modeled our simulation use cases, and today's demo will dive into the first simulation use case in a bit more detail. The demo starts on a project dashboard. This landing page gives you the possibility to observe tasks and configuration items that are assigned to you, the progress of your information objects, recent changes in the project journal, and a progress estimation via Gantt chart. In the Gantt chart, you can also depict delay and decide the scale on which the Gantt chart is going to be displayed. And if we look at the delay, we can see that the execution phase is somewhat in delay. So let's look into that by moving to the navigator view. Within the navigator, you have a structured view of all processes, phases, and activities of your project, as well as a graph view that shows additional information, such as configuration items and artifacts. On the very right, a detail view displays further information about the currently selected item. And here we can clearly see that the task to execute the simulation is still in specification. Scanning through the assigned artifacts and configuration items, all required information seems to be available. And if we want to make sure that the information is also sound, we can easily jump to the source system to check external resources, like such. With this check completed, the only thing that is actually missing to start the execution would be a guideline. But instead of adding a new guideline, we would like to reuse an existing one as an input. After the search interface opens up, we can select a pre-saved filters for methods. And this includes, of course, multiple guidelines, not just for simulation, but by scrolling through, we can easily find a simulation guideline that we would like to reuse. And now we can decide whether we want to reference to a very specific version or always use the latest one. Let's add the latest version and progress this task to be in work. Here we can hand over a message to our engineer that he shall start the execution and then progress the release workflow. By doing so, an automated baseline creation is being triggered, which you can see here. Such planned baselines can be created for specific events, like a defined activity entering the in-work step of the CSP workflow. This created baselines frees all attached information that is required for the simulation at the point of creation, and thereby ensures the possibility of resimulation. However, it would also be possible to add more information to the baseline, even going back as far as to the initial analysis. And since Tracy is designed to be a tool for traceability and not simulation execution, the engineer can now, as he has been informed that he is due to perform the simulation, export the project as SSP. The SSP container contains all information that is attached to the simulation task at hand, and thereby poses as a full and open information export from Tracy. Could you please stop the video? I'm not yet there. Thank you. Thank you. After some compilation time, the SSP package, including all referenced external resources, can be downloaded via the Tracy interface. This package is also stored on the connected GitLab server, so it can be downloaded from there as well. And after performing the simulation, for example, with Easy SSP, the user can upload an SSP container using the containing the simulation results, and by doing so, the project information is being updated in Tracy, and the incoming SSP container is stored on our GitLab server for traceability purposes as well. Now, assuming that Tracy can be used for several simulation tasks and projects, the amount of information in Tracy may become quite large. And to still be able to handle all generated and imported information, Tracy is equipped with a powerful search, as you have seen earlier. This search allows users to specify precisely what kind of information they are looking for. For example, after performing several simulations, I would be interested to see all simulation results that are deemed unsatisfactory. And now I would like to start the video, please. This requires more than just a text-based search, which we offer, of course, as well. So we are using Tracy's advanced search functionality. When doing so, we can reuse already saved searches or perform the last search again, as we have done just now. But for a full demonstration, we are now picking the entity type and expected qualifiers ourselves. This search returns quite a lot of results. And now the interesting question would be whether there are any results that are deemed unsatisfactory. Well, no worries then. Tracy allows me to perform queries on specific metadata fields. So let's refine this query to only return such results that have the simulation quality of unsatisfactory. There we go. Let's see, and we're down to one result. That's actually not bad, considering how many simulation results we just had in the previous search. With this, it is now time to show the possibility to perform trace analyses within Tracy. With the impacting entities analysis, we will show you that all entities that are somehow producing an impact workflow-wise on the observed entity. And if desired, we can extend it to show indirect impacts for the entire graph, as you have just seen now, which is kind of overwhelming. So let's go step by step and level by level. Right now, you can observe me scanning through the second level of detail and digging deeper to see where the issue for my simulation result is. I obviously didn't find anything on the second level, so I dug deeper into the third level. Here we already have significantly more items, but we also have this one configuration item called general requirements, which sounds kind of, there could be something on it. So we dig a bit deeper to see what the general requirements are depending on. And there we can see there's this one requirement, which we will look at in detail, and it is some embedded text, which has content in imperial units. Now, in this demo, our simulation is based on metric units, so we have some sort of issue here. And since we are enabling reuse, this item can be used in different projects as well. So I just started the where used analysis, where all of our projects and relations are being scanned through to identify any projects that are using this requirement in order to be able to inform the project managers that they probably want to look at this requirement because it might be not suitable if they are working with metric units. And this helps us to catch undesired and unwanted errors early on and reduce the impact of those. This would also conclude the demo of our traceability demonstrator Tracy, which ProStep is, as I already mentioned, continuing to develop as part of our product suite. The resulting product, OpenCLM, inherits all functionalities of Tracy that are being I just showed you and more. And if you are interested in OpenCLM, you can always contact me as the product owner or anyone at ProStep, really. We are very happy about this one and the results of set level in this. So on the next slide, I would like to conclude this presentation. And we would like the audience to take with you that we identified the need for simulation for the development and release of automated driving functions, just as much as we need to have consistent standards and data formats that allow for cross-application and cross-company collaboration. Preferably, a chain of tools could support the use case of standardized data exchange with this in mind. And exactly this need has also been demonstrated with our demonstration tools that can be used alongside the credible simulation process and that can communicate via STMD and SSP. In detail, Tracy demonstrates how the empowerment of users enabling them cross-application, cross-domain information tracing can produce credibility. By drawing baselines, resimulation can be ensured, information can be referenced instead of integrated, reducing redundancies and following the principles of linked data to create large information networks, which can then be utilized for powerful cross-project analyses. And on the very last slide, I would like to thank you for your attention. This is the last slide, sorry. If you would like to know more about our findings regarding the collaboration, about our traceability demonstrator Tracy, you are very welcome to visit us at our booth B19. And with that, I would like to thank you very much for your attention and give the word back to our very charming moderator.
Thank you, Anna.